His theories and ideas laid the groundwork for the digital revolution. From wartime cryptography to the modern cell phone, from electromechanical relays to the internet, his ideas made them all possible. Meet Claude Shannon, the father of information theory and a hero of the digital revolution. In the 1940s, Claude Shannon, a young research mathematician at AT&T's Bell Labs, was looking for a way to transmit communications more efficiently. At the time, telecommunications consisted of telegraphs, radios, telephones, and for a lucky few, the television. But they all had a common denominator: information. What Shannon realized was he could take any type of information and quantify it by assigning a source rate measured in bits per second. Shannon introduced his idea to the world in his 1948 paper, The Mathematical Theory of Communication. It set the engineering world on end.
His theory on communications, it just radically changed how people thought of how communications over wires, telephony at the time, occurred. It changed it from thinking that in order to get highly reliable communications, you had to slow the communications down, which, as we know today, with fiber optics and high-speed wireless, etc., would be a disaster. We wouldn't be doing it.
But according to Shannon, there were limits.
The realization by Claude Shannon that there's a relationship between channel bandwidth, power, noise, in order to determine how fast a transmission can communicate information, suggested that what you want to do is design with a consciousness of the Shannon limit, which simply says, how fast can I go given this amount of power?
You wouldn't have to transmit speech in a waveform. You'd sample it and convert it to bits, zeros and ones, and send the zeros and ones down a wire, and at the receiving end you would take these zeros and ones and build back a replica of the original signal.
The impact of information theory is all around us and continues to influence important research today.
I would say if you looked at AT&T labs today, you would find it difficult to find things that aren't, in some sense, a result of Shannon's theories.
Though his landmark paper was published in 1948, Shannon began making his mark a decade earlier as an MIT researcher and student. His master's thesis, a symbolic analysis of relay and switching circuits, has been hailed as the most important thesis of all time. Using and, or, and not logic, Shannon demonstrated how to combine Boolean algebra with binary arithmetic and apply it to electromechanical switching.
Relays in particular were relevant because they were used in telephony. AT&T had many relays because that's how telephones were controlled.
Because of Shannon's work, Boolean arithmetic is the basis for the design and operation of every computer in the world. While the bulk of his work encouraged communications, Shannon also devised ways to prevent some communications from ever taking place.
Claude Shannon was the first one really to make the connection between security and information theory. He saw them as intertwined. So when he wrote his paper, his landmark paper, Mathematical Theory of Cryptography, that was really an amazing contribution.
Not one to rest on his laurels, Shannon published yet another landmark paper in 1949, Programming a Computer for Playing Chess. A year later, he entered the field of artificial intelligence with his mouse, Theseus.
I'm Claude Shannon, a mathematician here at the Bell Telephone Laboratories. This is Theseus. Theseus is an electrically controlled mouse. He has the ability to solve a certain class of problems by trial and error means and then remember the solution. In other words, he can learn from experience. Like his classical namesake, Theseus has the problem of finding his way through a maze. His objective is the goal here in the corner. He is now exploring the maze using a rather involved strategy of trial and error. As he finds the correct path, he registers the information in his memory. Later, I can put him down in any part of the maze that he's already explored, and he'll be able to go directly to the goal without making a single false turn.
His brilliant ideas did not stop there. On his desk, he kept a box he called the Ultimate Machine.
It's an amazing machine. It's a box, it's a wooden box, and it's totally featureless except for a single switch. So you throw the switch, and a lid opens up, and an arm comes out of the box, a mechanical arm. It looks like a real hand, and it turns off the switch, and the arm goes back into the box, and the lid closes. And that's it.
You know, there's a playfulness in great researchers that you see all the time. Sometimes we would see it as a little quirky. In Shannon, you saw it in all of his little hobbies and interests, building a mechanical mouse and building a juggling machine and riding his unicycle around the labs always. It's one of the more charming elements that we all remember when we think about Claude Shannon.
Shannon left AT&T in 1956 with his bride Betty, a Bell Labs numerical analyst, to teach at MIT, and retired in 1978 to pursue his other passions. They included juggling and building gadgets like a gasoline-powered pogo stick, a robot that could solve Rubik's Cube, and his throwback machine, a computer that calculates in Roman numerals. His awards include the National Medal of Science, Japan's Kyoto Prize, and the IEEE Medal of Honor. He's a fellow at AT&T, MIT, UCSD, Princeton, and IBM, to name just a few. But perhaps his biggest honor is in Florham Park, New Jersey.
I think everybody here is really proud that the research labs here are named after Shannon. It's hard to think of anybody who had more influence on the kinds of things we do here. And it's hard to think, frankly, about what kinds of things we would be doing had he not done the things he did.
Shannon reflects on his life's work in information theory.
I didn't think in the first stages that it was going to have a great deal of impact. I enjoyed working on this kind of a problem, as I have enjoyed working on many other problems without any notion of either financial or gain in the sense of being famous and so on. And I think, indeed, that most scientists are oriented that way, that they are working because they like the game.
Dr. Claude Shannon was a scientist, engineer, founding member of the Unicycling Society of America, and the father of the information age. But his passing in 2001 did not leave a gaping hole in the world of mathematics and engineering. Instead, it left an open door, a door to creativity, innovation, and the possible. And that is why Claude Shannon is not only a tech icon, but a hero of the digital revolution. Without him, cell phones wouldn't be all that handy, and long-distance billing would still be tallied by hand. Meet Amos Joel, mobile phone pioneer, father of modern telephone switching, one of the original phone freaks, and a tech icon. Users of the first working cell phones were limited to only calling people in their cell site. That's because as they moved to the edge of their cell, the signal diminished. And when they entered another cell, the signal was incapable of following.
Without being able to use your phone more than a few miles from the center of the cell, then it wouldn't be worth much when you went to the store or if you were driving off in your car. It would be handy to have it, but it'd be sort of like having a cordless phone in your house as opposed to something you could take with you anywhere in the world.
Amos changed all that in 1972 when he devised a way for cells to hand off calls. So when people move away from one cell and the frequency becomes too weak, the cell can coordinate with adjacent cells, hand off the frequency, and provide uninterrupted coverage. With more than 70 patents to his credit, Amos's place in history goes well beyond cell phone technology and includes the Bell System's automatic message accounting system.
AMA, or automated message accounting, is mechanization of the billing process that involves a lot of different small transactions usually, so it has to be done very efficiently, but it also has to be done very accurately.
Before AMA, long-distance calls were completed by operators. They asked the caller the number they were calling from, the number they were calling to, and recorded the information before making the connection. But some people discovered that if they purposely provided the operator with the wrong originating number, someone else would get the bill. So Amos developed AMA, a system that used electronic switching methods to automatically identify the originating number. The system recorded the information on punched paper tape. A computer then used that record to generate an accurate long-distance bill. Amos's AMA patent also holds the honor of being the largest patent ever, weighing in at an incredible 11 pounds.
It's one thing to have a vision, say, well, we could do AMA recording, and it's another to grind out the 500-page patent that really makes it work.
Another of Amos's ideas combined computer technology with electronic switching to replace the switchboard. It was called Traffic Service Position System, or TSPS. Now, operators no longer needed to be geographically close to the customer. A person only needed to dial 0, and they would be routed to a centralized call center from anywhere in the country. This was a huge step up for the network Amos loved since childhood.
Well, Amos, from the time he was 10 years old, wired up a private little telephone network in his apartment in New York based on telephone equipment that had been taken out in the Depression by people who unfortunately couldn't pay their telephone calls. So he got access to that and wired up his own little private telephone switching system.
One of the incidents that I remember the most, a friend and I were sitting in my apartment, and all of a sudden the telephone bell rang. We couldn't figure out who it would be. So I answered the telephone, and the man at the other end said, "This is the telephone man. Where are you located?" He didn't like the fact that we ran the telephone wires down along the cables in the back of the fences where the telephone company wires were. So we had to give our telephones back to the telephone company.
Amos's fascination with the phone system continued, and his lifelong dream of working for Bell Labs was realized during World War II. He first collaborated with Claude Shannon on early digital cryptanalysis machines, before focusing on switch engineering. He retired 43 years later, but continued to consult with the labs, write, teach, and lecture about switching systems.
What's important about Amos and the work he did is that he had the vision of what needed to be done, and he did it and carried it out.
Awarded the IEEE Medal of Honor, a Kyoto Prize, and the Alexander Graham Bell Award, Amos was also inducted into the National Technology Hall of Fame for his vision, inventiveness, and perseverance in the advancement of telecommunications. And that is why Amos Joel is not only a tech icon, but a hero of the digital revolution. His discoveries validated the Big Bang Theory and are central to the study of star formation. Robert Wilson, physicist, cosmologist, radio astronomy innovator, and a tech icon.
My career has mostly been building instruments for astronomy, and I've had the good fortune to use them on some projects which turned out very interesting results.
Projects like this one in 1964 when, along with fellow scientist Arno Penzias, Robert Wilson made a discovery that earned them a Nobel Prize and a place in history. That project began with a radio telescope called the Horn Reflector Antenna. It was located at Bell Telephone Laboratories in Homedale, New Jersey, where Wilson and Penzias worked. Originally constructed in 1959 to support early satellite communications, the 20-foot horn antenna was largely obsolete when Wilson and Penzias asked to use it to listen to the cosmos.
What we were going to measure was radiation from gas in the Milky Way galaxy. And that gas does not produce optical radiation. So if you go outside and look, you won't see it. Even if you look with the Hubble telescope, you won't see anything. In fact, one of the components is just hot electrons that are moving in a magnetic field and radiating. So this could produce a low level of radiation that the 20-foot horn reflector was ideal for measuring.
Before it could be used for their radio astronomy experiments, the scientists had to design and build a system that would allow them to calibrate the horn antenna's receiver.
Well, as soon as we put our whole accurate measuring system together, there was a big problem because we were seeing about an extra 3 degrees of radiation.
That difference was significant.
So much so that we could not believe that the galaxy was causing it, and we at first thought there was something wrong with our equipment, of course. So one of the things we did was turn our sensitive instrument down, look at the horizon, and scan the horizon, including New York City, to see if there was a lot of excess radiation beyond the thermal radiation the Earth would have. And no, there wasn't.
Still stumped by the extra 3 degrees of radiation, the scientists spent months trying to pinpoint its origin.
We looked out of the plane of the planets to see if it had anything to do with the solar system. We looked away from the Milky Way to see if it had anything to do with our galaxy. But there was nothing out there.
They looked for interference closer to home, even at the pigeons living inside of the horn.
We got up there and scraped the pigeon droppings out. That made a little difference, but not a significant difference. Clearly, it wasn't pigeon droppings.
That's when they realized the noise was coming from outside our galaxy.
The explanation was one of those accidents that occur in science.
What they had discovered was cosmic microwave background radiation, or CMB. In effect, the remnant noise from the creation of the universe as described by the Big Bang Theory. The Big Bang Theory suggests that the universe began as a hot, dense fireball that erupted over 13 billion years ago. Big Bang theorists believed that radiation from that event would still be detectable, and in 1964, a group at Princeton University had begun to search for it. It was only when Wilson and Penzias heard this and shared their findings with the Princeton group that the two recognized the significance of their mysterious 3 degrees.
The discovery of the cosmic background radiation is something that, I can look back and say there's a specific record in 1964 when we first saw it, but we didn't understand what we had.
Wilson and Penzias published their results to an eager audience. Recognition followed, and more than a decade later, reward.
Sharing the 1978 Nobel Prize for Physics are Arno A. Penzias and Robert W. Wilson of Bell Laboratories.
I had a couple of immediate reactions. One was, oh my God, I've got to give a Nobel lecture. The other one, well, it just was amazing to be put in the company with all of the other people who have won Nobel Prizes. I don't think of myself that way.
After their Big Bang discovery, Wilson and Penzias continued developing receivers, eventually putting one to work in Arizona in search of interstellar molecules.
We built the most sensitive receiver we could make. We realized that we had an instrument which could do something that no one had ever done before. We fought for 5 days getting it all to work together.
And then Robert Wilson had what he describes as his eureka moment.
We put it up on the antenna, and with a 2-second integration time, we saw the signal. What we really discovered was the existence of giant molecular clouds, which explained all the star formation that goes on. And that provided the tools for studying star formation in the universe.
The perfect culmination of years of tinkering with electronics and astronomy.
When I was growing up, I fixed radios for people. I learned all about the vacuum tube radios and how they worked, and learned how to fix them. And later, televisions came. They were vacuum tube televisions at the time, so a lot of the same techniques applied.
Wilson is now at the Smithsonian Astrophysical Observatory, working with a special receiver called a submillimeter array, or SMA.
The SMA is a general-purpose instrument. It's been used to look at the dust disks which surround young stars. the sort of disk that would probably form a planetary system. An experiment which is coming up will be to use it in what we call a very long baseline interferometer, where we record signals in Hawaii, someone in California may record signals at the same time, someone in Chile, maybe even at the South Pole. Put this all together, you have an Earth-size radio telescope, and we should be able to see into the black hole at the center of the Milky Way galaxy. Cosmology is headed toward understanding the gap between the time the cosmic background radiation was released and the time the earliest stars and galaxies have been observed. There's a transition in there which has not been measured. One can speculate that maybe stars formed and then they collapsed into galaxies. It could have been the other way around.
Wilson's interest in astronomy began with a desire to learn.
When I started in radio astronomy, I was drawn by the interest in astronomy, the physics to be learned, and the fact that I could use my interest in electronics.
Now, with a half-century of discovery behind him, Wilson's quest continues. It's that pure passion for learning and science that makes Robert Wilson, thought leader, visionary, and Nobel Prize-winning radio astronomer, a tech icon, and a hero of the digital revolution.